Page 16 of Chapter 16, Euler's Complex Numbers of MathHL. So we're continuing the problem that we just did on the last page, which was we found the 5 fifth roots of unity and displayed them on our Venn diagram, and we showed that the roots are 1, omega, omega squared, omega cubed, and omega to the fourth. Now, C says to simplify this polynomial. So let's do a distribution of 1 minus omega times that expression. So we're going to get 1 plus omega squared plus omega cubed plus omega to the fourth. And then we're going to add that to the minus omega times each one of these. So it'll be minus omega times 1, minus omega times omega, minus omega times omega squared, minus omega times omega cubed, and minus omega times omega to the fourth, which would be minus omega to the fifth. And then if we add all these together, all these will cancel out, and the first term and the last term will remain. And we have 1 minus omega to the fifth. And if we figure out what that is, actually omega to the fifth, remember, omega is the fifth root of unity. So omega to the fifth is unity. So it's 1 minus 1 equals 0, right? So this big expression is actually equal to 0. So if this is equal to 0, then by the zero factor rule, either the first factor must be 0 or the second factor must be 0. And we know that 1 minus omega is not equal to 0, right? Because omega is a complex number that is not 1. So when you add it to 1, you get a non-zero number. So we know that that is not 0. So that means that the first term factor must be 0. Okay? Now let's show the same thing by vector addition. If we take 1 looks like that. Omega, remember, looks like that. 2 pi over 5. It's kind of like, I'm going to move this down a little bit. 2 pi over 5 is about like that. And then 3 pi or 4 pi over 5 is about like that. And then 6 pi over 5 is about like that. And then 8 pi over 5 is about like that. And do you see how it makes a perfect pentagon? My drawing is not a perfect pentagon, but if you do vector addition with these 5 vectors, they will come back to the exact same position you started with. It forms a regular polygon. So that's why if you add up 1 omega, omega squared, omega cubed, and omega fourth, you get, you arrive exactly where you started from. Let's go to 16G, which are the chapter ending problems, the miscellaneous problems. Solve for z. So we got z squared minus 2 plus I, which is the b coefficient, and we have 3 plus I, which is the c coefficient, equals 0. Okay, so remember that we can always find the roots to a quadratic by doing quadratic formula. So in this case, let's say b is equal to negative 2 plus I, c is equal to 3 plus I, and a, of course, is equal to 1. So we could do quadratic formula here to solve for z. Z is equal to negative b, so that would be 2 plus I, plus or minus square root of b squared, so that would be 2 plus I squared, minus 4 times a times 3 plus I, all divided by 2. So let's see if we can simplify that a little bit. So we have 2 plus I divided by 2, plus or minus. And so the square root of, let's see, 2 plus I quantity squared would give us 4 plus 4I plus, or minus 1, because I squared is minus 1. Then we have minus 12 minus 4i. And that's over 2. So now we got 2 plus I divided by 2 plus or minus, and let's see what we get in here. So like, do you see how the 4i and the negative 4i cancel? And so now we have 4 minus 1 minus 12, which would give me negative square root of negative 9 divided by 2. And so this is equal to 1 plus 1 half I plus or minus, and square root of negative 9 is 3i, right? So 3 halves I. So the two solutions are 1 plus 1 half I plus 3 halves I, which would be 1 plus 2i. And the other solution would be 1 plus 1 half I minus 3 halves I, which would be 1 minus I. So those would be the two roots here. Let's look at number 2. Find the Cartesian equation for the locus of points p of x comma y if z equals x plus iy and z conjugate equals minus iz. Okay, so let's, instead of z conjugate, we'll write x minus iy because that's the conjugate of z. And then for the other one, we'll write negative I times x plus iy. And then we'll multiply out the second one. So we'll get negative ix. And then I squared is going to be negative 1, so it'll be negative negative 1. So it'll be plus y. And then we're going to equate the real parts and the imaginary parts. So the real parts would be x equals y. And the imaginary parts would be negative y equals negative x. Right? Yeah. And so basically the first statement says the exact same as the second statement, that x is equal to y. So the locus of points is just when x equals y. Let's look at B. So for B, it says when the argument of z minus I equals pi over 6. So that would be, so z minus I would be x plus iy minus I. And when would the argument of this equal to pi over 6? Well, let's first make an expression with a real part and imaginary part. It looks like that, right? So the imaginary part would be y minus 1. The real part would be x like before. So basically what we're saying is that the ratio between the vertical part, y minus 1, and the horizontal part, x, would have to be the tangent of pi over 6. The tangent of pi over 6 is going to be 1 over square root of 3, right? So we'll say that must equal to 1 over square root of 3. And so let's try to solve for y here. So we have y minus 1 equals 1 over square root of 3 times x. Y equals 1 over square root of 3x plus 1. So that kind of forms a linear equation with a slope of 1 over square root of 3 and a y-intercept of 1. What about C? So C says the modulus of z plus 3 plus the modulus of z minus 3 would equal to 8. So in this problem, I have to be honest with you, the first thing I did was I substituted x plus iy in for z, and I started trying to simplify. And the thing became enormous. So after a while, I checked the book, and the book said, do not substitute in x plus iy in for z. The only other thing we could do if we don't substitute an x plus iy in for z is if we try to expand it just using the other definition of modulus, which is that it's the contents times its conjugate, right? So let's try to do that. So we're going to have z plus 3, and that's equal to 8 minus z minus 3 conjugate. And then we're going to square it. We're going to square both sides so that we end up with expressions that have modulus squared, so that we can make them into like complex number times complex number conjugate, right? Because remember, if we have a complex number squared, that's equal to the complex number times its conjugate, right? So we need to like try to use that identity. So we need to get this to a situation where we have modulus squared. So let's square both sides. If we square both sides, the left side is going to be very nice. It'll be z plus 3 squared. And the right side is going to be a little messy. It's going to be 8 minus z minus 3 squared. And so the left side is going to be basically what we want. It'll be z plus 3 times z plus 3 conjugate. And the right side is going to be messy. It's going to be 64 minus 16 conjugate z minus 3 plus z minus 3 squared. And so z minus 3 modulus squared could be written as z minus 3 times z minus 3 conjugate. And so the left side, z plus 3 times z plus 3 conjugate, that could be rewritten as z plus 3 times z conjugate plus 3, right? Because 3 is a real number, so if we take the conjugate of the two things added together, it's equal to the conjugate of the first one plus the conjugate of the second one. But 3, there is no conjugate because it's just a real number, so we get z conjugate plus 3, right? And then we'll get 64 minus 16, and then z minus 3 conjugate. We can't do anything about that because it's not squared. And then we get plus z minus 3, z minus 3 times z minus 3 conjugate, which would be equal to z minus 3 times z conjugate minus 3 by the same reasoning that we used before, right? Now we can FOIL these expressions. So we'll have z conjugate plus 3z conjugate plus 3z plus 9 equals 64 minus 16 times z conjugate, or z minus 3 modulus, plus z conjugate. Now you can start to see why maybe we're going to get rid of some terms. Minus 3z conjugate minus 3z plus 9. Now we can cancel out some stuff. The 9's on both sides can cancel out. Z conjugate on both sides can cancel out. Let's add together the common terms. So minus 3, we add 3z to both sides and we'll get 6z. We add 3z conjugate to both sides and we'll get 6z conjugate. And that'll be equal to 64 minus 16 z minus 3 conjugate, or 3 modulus. Now that we have this relatively simple expression, let's substitute in z equals x plus iy. So this will be 6 times x plus iy plus 6 times, 6 times x minus iy equals 64 minus 16 square root, and this will be x plus, so like, let's do this. Z minus 3 modulus is equal to x plus iy minus 3 modulus, which is equal to x minus 3 plus iy modulus, which is equal to x minus 3 squared, it's Pythagorean theorem, plus y squared, square root. So this left side is going to be 6x plus I6y plus 6x minus I6y. And then look at that, the I6y and the minus I6y cancel out. So we end up with 12x on the left And now we're getting to the point where we can remove the root sign by squaring both sides. If we just remove, if we move 64 to the left side. So we're going to put 12x minus 64. And then on the right side, we'll have negative 16 root. And then we could make this a little bit complex, divide everything by a common factor of 4. So then we end up with 3x minus 16 equals negative 4 root. And now we could square everything, right? So then we could say 3x minus 16 squared equals negative 4 squared is 16. So the root squared would be the inside of the root, which would be x squared minus 6x plus 9 plus y squared. Now we can expand 3x minus 16 quantity squared. That would be 9x squared minus 96x plus 16 squared, which would be something like 256 equals 16x squared minus 6 times 16, which would be something like 96x, 9 times 16, which will be something like 144, plus 16y squared. Now I can cancel out the 96x's here, and I can combine like terms maybe. So I could get 7x squared. 144 minus 256 gives me a minus 112 and 16y squared, and then I end up with 0 on the left side. And I could make this into kind of like a conic. It would be like an ellipse. It would look like that. So that is a relationship between x and y, which is an ellipse, and that would be the solution to this last one. Okay. And that's it for this page.